Okay, today we're going to talk about electromagnetism. It is, I believe, the second last lesson for the unit and for the course. So we've been talking a little bit about electric fields, a little bit about magnetic fields, and now we're going to join them together. So prior to the 19th century, so that was the 1800s. So prior to the 1800s, people thought that electricity and magnetism were separate and distinct. However, there were still lots of natural philosophers, so thinkers, who wanted to discover a connection between the two. Hans Christian Ørsted, he was a professor of physics at Copenhagen University, that's in Denmark. He believed for a long time in what he called the unity of nature, so he thought everything was connected, and philosophically he thought there should be a connection between magnetism and electricity. So he actually kind of discovered the connection by accident, as many things have been discovered in science, accidentally. There was a wire leading to a voltaic pile, so a voltaic pile was like a really basic battery. There was a compass laying by this wire, and the compass was changing directions as the circuit was altered. So when the circuit was closed, so that means there was a path. If you remember from grade 9, it's confusing. A closed circuit sounds like it should be off, but it's actually on. So when the circuit was on, or electrons were flowing, the needle swung perpendicular to the wire, okay? So here's our compass here. It would have swung perpendicular to the wire. So open switch is off. But when it was on, it would go completely perpendicular to the wire, so at a right angle to it. Okay? So Ørsted actually formulated the basic principle of electromagnetism, where he said that moving electric charges, like an electrical current, produce a magnetic field. Okay? So when the current is turned on, there seems to be a magnetic field. So Ørsted's discovery made its way to Paris. So it took a little bit of time, from July until September. And then you might recognize ampere. That's what we actually measure current with, is an ampere. So this person, he saw what had been done, and he was kind of motivated or inspired to do some experiments of his own. So ampere showed that the magnetic force experienced by a compass acted at right angles to the current. So if your current is going one way, the magnetic field was at a right angle to it. Okay? So this diagram here kind of shows the relationship. So as the current went one direction, the magnetic field was perpendicular to it around. So if this is your current, the magnetic field was all around, but consistently at right angles to that current. Okay? So when there's a current present, there is a circular pattern around the wire. So as you place the compass at various locations around the wire, it kind of points in a circle. And if this is your current, it still points at right angles at any direction, just pointing in the direction of a circle. If you reverse the direction of the current, so if instead you had the current coming down, the direction of the magnetic field also switched. So instead of kind of going in this into the page, out of the page, it would go the opposite direction. And as you move further from the wire, magnetic field intensity decreases, which makes sense. The further you are from Earth, the less gravity. The further away you are from an electric charge, the weaker the electric field. Okay, so we have something called the right-hand rule. Now, I've never done this on video, so this should be very interesting. Basically, you need to use your right hand. If you forget which hand is which, do the L thing. If it shows an L, that's your left hand. We do not want your left hand. If you use your left hand, you will have everything backwards. So essentially, if you take your hand and make a fist and point your thumb out, your thumb and your fingers show the direction of the current and the magnetic field. So the thumb points in the direction of the current. So my thumb is pointing to the left, that's the direction of the current. Now your fingers, imagine them curling around a wire. Your fingers are pointing in the direction of the magnetic field. So it kind of goes in and then comes out through my hand and then goes in at the top and out through my hand. So this diagram also helps. The current is going to the left, the magnetic field is going into the page above the wire and coming out. So of course this is really hard to show or explain on a 2D surface like a paper. So what we have is we use these crosses and dots to symbolize the current going in or the current leaving. So we use a circle with a cross or an X, and we use a circle with a dot. When you see a circle with a cross, that shows current going in. Okay, so up here we have current going in and coming out. So it's kind of making a circle in this direction. Okay, in, out, and current is going to the left. If we reverse the current, so current is now going to the right, the magnetic field is entering at the bottom and coming out over on top of the wire. So the cross represents in, so your thumb would be pointing this way. Your thumb is the current, and your fingers would be wrapping around this way, showing that the magnetic field is like coming at you over the wire and going away from you underneath the wire. Okay? So this scenario here shows this, whereas this scenario here would be the opposite case, so thumb pointing to the right. Okay? This is definitely weird. I always joke that when people are trying to figure out direction of stuff, you just kind of see them staring at their hand, like flipping their hand around. It's pretty entertaining for me. So we can also have magnetic fields with a loop. So when a straight wire is wrapped into a loop, the magnetic field can appear in different ways. So this diagram here shows the loop of wire in a horizontal position. Okay, we have the current coming this way, going around, and then exiting to the left. So what happens is on this side of the wire here, I've drawn it down here to kind of make it clear for us, we can see that the arrows are representing the magnetic field. So they go in underneath the wire and they come out over top of the wire. So in below the wire, out above the wire. So this diagram here shows the magnetic field going in underneath the wire and coming out on top of the wire. So it's like if you put your hand on the loop of wire like this and just kind of like went around the circle with your hand on it, that's what it would show. Now part of me wishes I had a loop or something to show you. So let's say this was my loop of wire. It's my phone charger. Let's go a bit higher. So if the current is going to this direction, so underneath the wire, the current is going in. That's what we represent with X's. And above the wire, the magnetic field is coming out. So we represent that with dots. And then if you kind of like took your hand and went around the loop, you'd notice that the whole way around, underneath the wire, you have the magnetic field going in, and above the wire, you have the magnetic field kind of like going out. Okay? Again, this is really hard to actually demonstrate without being in front of people. So remember those crosses, they represent the magnetic field going in, and then the dots represent the magnetic field coming out. Okay? Magnetic field of a solenoid. A solenoid is a very, very long conductor wound into a coil with many loops. The magnetic field of a solenoid, you have to add the magnetic fields for each loop. So they're very, very strong. There's lots of field lines that are very straight, very close together. So close together means strong. So to determine the direction of the magnetic field, use the right hand, just as we did with the straight wire and the loop. Okay. This time, what we're gonna do is reverse the right hand rule. So your fingers are going to represent the current, and your thumb is going to represent the magnetic field, okay? Because when we have a solenoid, the current is now looping around. So it doesn't make sense to use our thumb as the current because our thumb is not looping around, but our fingers are. So if we have, in this case here, we have the current coming down, going under, and then at you above the wire, basically. So if the current is coming in, over, and then going away, we'd want to have, oh my goodness, we're going to be kind of like going under, and then the current is coming back up over top of the solenoid. So it goes in under, and then comes back over top of it. So our thumb is now pointing in the direction of the magnetic field, which is to the right. And that also makes sense because if we remember from our magnetism lesson, we have the field lines exiting the North Pole and entering the South Pole. So a compass, or the direction of the magnetic field, would point out the north side of the magnet and then in the south side of the magnet. Okay, so this is more of a picture diagram. This is what we would use with symbols. So we have the north and we have the south. So our magnetic field would be pointing to the right, and then our current goes in and it comes out above it. Okay. So here again we have a diagram with a hand. So the North Pole is to the right, so our magnetic field direction is to the right, and then we would have the current coming up and over the wire. So yes, this time your fingers will wrap around in the direction of the current, and your thumb will point in the direction of the magnetic field. Okay? So solenoids have magnetic fields very similar to that of a bar magnet, because one side is where the field lines are exiting, one side is where the field lines are entering. But the cool thing about a solenoid is that you can turn it on and off. So if you stop the current flowing, there is no electric field, there is no magnetic field. Okay? And note where the lines enter is the South Pole, and where the lines emerge is from the North Pole. And this came from lesson 4. So electromagnets are current-carrying coiled conductors. Really cool alliteration. So a solenoid is an electromagnet. Okay? There are several factors that can affect the strength of the magnetic field inside of an electromagnet. The material, for one. If you use a piece of ferromagnetic material, such as iron, the magnetic field is much stronger. Okay? The domains in the iron would be aligned by the magnetic field in the coil, and the total magnetic field is summing up all of the fields. So the total field can be thousands of times as strong as that of the coil alone, which is really cool. If the size of the coil is smaller, then the field strength is more concentrated and therefore stronger. If you increase the number of coils or turns, field will also increase. And then if you increase the electrical current flowing through, that will also be stronger. Okay? So uses for electromagnets, they can be used to lift things. So lifting cars at shops or junkyards, they often use an electromagnet. Bells and other electronics make use of electromagnets, and they can also be used to generate power. Okay? If you have a turbine or a windmill or like a water wheel turning, you can convert that into electric power. All right, awesome. Thanks for watching.